And good morning. Welcome to Math in the Morning. And welcome everybody. Thank you so much for joining us here today. Alright guys, I was very surprised on the last video that I posted because usually I get like 5 views and I'm the one that's watching them. So thank you for watching. So you guys did like my Killing Primes. Thank you so much for watching. So today I wanted to talk about what I do this week. How's your week going? How did your week go? My week was great. What I worked on this week was Vopenka's Principle. So if you've probably already seen it, if on Substack, I made a post about Vopenka's Principle. So I just want to go through that. And then also I wanted to talk a little bit about the nature of existence, because I think there's like some major confusion. Well, I mean, this is on my opinion, but I think that like, I'd rather just talk about the nature of mathematical existence, but I think it kind of bumps up against, the physical world, and so you have to think about that. So I would like to talk a little bit about the nature of existence at the end of this. Okay, sorry guys, I got the news reporter. It's all going to my head. Okay, so yeah, let's talk about Vopenka's Principle. So I'll just put up the first picture that I have from the paper. So this is part of chapter 4. So each chapter in the book is usually like 4 parts. There's like 3 parts. There's kind of like a reasoning for each part, but like the middle one is sort of the big guy, and like there's lots of images, and then the third one is more like a creative thing, like maybe it's a play or something. And the 4th part is a play. But for chapter 4, well, Carmody's been writing it, so chapter 4, there's 10. I thought it would be easier to do 10 pieces, like 10 shorter pieces instead of 3 bigger pieces. But it's made it just last. It's just been taking a long time. But I really like that. I really like it. Every time I write when I write this one, I was like, this is my favorite so far. So I do like that feeling that when I feel like, oh, this is my favorite one so far. Because I always feel like that. Not always, but okay. So this one was about Vopenka's Principle. So so far we've gone through, this is the number 6 large cardinal of all time. And so we've already done 10, 9, 8, 7. Okay, so this way, after I just posted that, I'm halfway done with the book. Okay, the book is I've been working on it for 2 years now, and so I made a schedule for myself. Kind of what I've been doing lately is a little bit, I picked up the pace a little bit, and so I think that I can be done in a year. So I think that even though halfway done, I think that the next half can be done in a year if I keep up with my schedule. So that'd be great. It's so weird writing a book and you think about time so differently, because it doesn't seem like it's been 2 years, and this is what I've been working on. I'm definitely gonna take a year off from writing a book after I'm done with this book. I'll probably write another book. I don't know. Maybe this is my only book. Yeah, so it's really different. You think about time really differently, like in terms of months. Like November is not that far away because it's only like, a few posts away. Okay, so we're talking about Vopenka's Principle. I always really like Vopenka's Principle. I love the statement of it. And I don't know that much about it, but I really like the statement of it. It just seems so romantic. And so the statement of, so let's go on to slide 2. Sorry, I'm not talking. So let's go into slide 2. So Vopenka's Principle, this is from Yek. Let C be a proper class of models in the same language. Then there exist 2 members, A and B, of the class, such that A can be elementary embedded in B. And that's from Yek. And Yek was Vopenka's student. And Yek wrote the best book of all time. Okay. So I wrote a story about, I like to use these theater analogies. And I also think it's somewhat to do with the nature of existence. And like, I always like when I've read like philosophers have this kind of wild idea for how things work. And so I try to throw some of those in there. It's partially just that you have something really to hold on to remember, but maybe it's cool, some like, maybe like thoughts on the nature of existence too. But mostly it's a story. And so the idea is that if you have a scene is like good or works if it's true in the model. And so with that analogy, we think of these models as like theater companies, and they have the players, the actors, those are like the number universe. And then we talked in another section, I talked about casting directors being like Skolem functions. So there's all kind, I think it's a great, I think it's a useful analogy, and I think other people can use it. Okay. So, the idea, I'll let you read it, but A elementarily embeds in B means that A is isomorphic to an elementary submodel of B. Okay, and then later there's a picture. Okay, but I'll let you guys read this. Okay, But the idea, and I do believe this. I think we're safe here. I think, our actual true selves are somewhere safe. And I say no one really dies. One can always be recreated in the eternal world via their isomorphic copy. So the idea with the embedding is that, like, because of Vopanka's principle, we get these two models, and we can sort of keep one. We kind of keep both actually in the eternal world, but we can keep one as like a backup for the other in case something happens. It can be regenerated. That's what I think. So it's sort of like a safety measure of the universe, of the creation before something gets put in the physical world. You guys, I don't know. I think I've like read a couple of philosophers, like maybe Hegel, is that a thing? I don't know. There's like a river or something. I just like these like wild philosophies, so I kind of try and throw those in there. Okay, this is the way it's been since the beginning, and this is the way it will always be, thanks to Vopanka's principle. Okay, slide 3. So I always pick a paper for the large cardinal sections, and this paper I picked was Joel David Hampkins, my advisor, my former advisor, when he was at CUNY and I was at CUNY. But the paper is, the Vopanka principle is an equivalent to, but conservative over the Vopanka scheme. And so when the first thing someone might notice with the Vopanka principle is like you're quantifying over classes. And so that's a second order statement. And so he shows that they're actually not equivalent. There's like a Vopanka scheme, which is like a first order version, like a scheme version. And he shows that they're not actually this. You can have one fail. You can have the principle fail and have the scheme be true, but that they have, this is a quote, have exactly the same first order consequences in the language of set theory. Okay, so we got that. And then let's go to, and then also I wanted to show Vopanka's principle implies a lot of other large cardinals. And like, I think one of the most obvious ones is the one extendable cardinal. And so this was like a proof outline maybe of us showing that Vopanka's principle implies there's a one extendable cardinal. And the basic idea is just consider the class of all models V sub alpha plus 1 with the language of set theory with epsilon for alpha and ORD, and then two of them have to embed in the other, and then you can like restrict that to get a witness for one extendable cardinal. Okay, great. And then, okay, so let's go to 4. So the philosophy of Vopanka's principle, I'll let you read this. So let's see if can you figure out what it's saying? Okay. I wanted to write something that was in like another language. Like I wanted to do like modern Shakespearean or something, but that was really hard. I couldn't like figure it out. So I did this where it's like I just made like a code for I use like numbers and letters, so it's kind of hard to read. But I guess the idea is that I'll let you read it because you tell me. I think now I'm really thinking highly of myself here, or the book. But I think it would be cool in a class that was a little more like a discussion class, maybe a philosophy class, if they could be like, okay, let's read the philosophy of Vopanka's principle. What is it saying? It could be an assignment, like a discussion topic. What's it saying? What does it have to do with Vopanka's principle? Maybe someone could come up with something that's even better than what I even originally intended. So, but the idea is that these two people are at this big party, and they're just so they're sort of connected. And what is I think interesting is that they're connected. They're connected on the inside. They're connected non-superficially, like not on the surface. It's there's something on the inside that they are able to, they're connected in their cores. They're connected in their cores. And so that's what I think of Vopanka's principle. If you have no idea what math is or any, what Vopanka's principle is, or you think, oh, I don't know anything about math. I think of it, it's a sea of people, and there's two people that are always going to be super connected. And that's so romantic. So I hope you enjoy that. Let me know, what does it say? And then we have the picture here, just showing the different levels, and there's the eternal world, there's the pre-physical world for extra safety measures, and then there's the physical world, and then there's the true home of the actors. And I like to kind of mix like the actual math with like this other stuff, so it all seems like serious. It all seems like it has the same level of seriousness. It's for fun. Okay. Further research. So I was thinking about this, and like I just want to it's like kind of, what can I say that's connected to anything I'm interested in, and so I just want to talk about abiding cardinals. Abiding for one extendables just means you're a target of a one extendable cardinal, and that Vopanka's principle 3, which I don't know, I don't know if this is around or if it even makes sense, but what if there were 3 models, one embeds in the other, and they do it in like a cohesive way? So the critical point of this one, the critical point of the first one is kappa, the critical point of the second one is J of kappa, so that they are cohesive. Then we can get one extendable cardinal, which is also a target of a one extendable cardinal, guaranteed. So I thought that was fun. Okay. Okay, so you can read that and let me know what's your favorite consequence of Bopanga's principle. I know that Bopanga's principle has like category theory. I don't know anything about it, but I think there's some people that are interested in it in like different areas. And then the references. Okay, great. So I hope you like that. Thanks so much. I say thanks so much, but just thanks for letting me talk about it. Thanks for reading it. Like, I was watching some like Lena Dunham interview from a long time ago, and she was like, what's the hard part about being a writer? And she's like, it's so lonely. But you know what, this isn't lonely at all. So cause I get a, it's like a reward that I get to come and talk to you guys after working on this stuff. And I love Substack because I just get to share it immediately. So it's like, I know that the editing is going to be hard and stuff, but okay. So you guys, let's talk about the nature of existence real quick. Thank you for listening. I think it's important to talk about just really quick. Maybe this should be a whole other segment, but I've talked to like very, 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 very smart philosophers. This is like at a conference, like not anyone I really knew that well, but just it's a vibe. Very smart people from very good universities telling me that the continuum hypothesis, because it's connected to physical reality, has to have a definite truth value. There's like a whole, it's like a whole rumor going around that like the continuum hypothesis is still like up for debate, and like we're still trying to figure it out. It's like they don't really believe Gödel, and they don't really believe Cohen, and it's just, I think it's like the truth is so much more interesting than like, maybe it just takes some time for the message to get along, but like, and Joe Hampkins wrote a whole paper about how the continuum hypothesis is settled. And I mean, okay, I don't have to talk too much about, I think sometimes people think that like, I don't know, like maybe it's his fault that there's this independence phenomenon, but like, I feel like there's so anyway, the point is that like, I don't think that, because I don't know if I was kind of going on a tangent there, I might have lost myself. So that this thing I was talking about, it's Sierpinski's theorem from 1919. CH is equivalent to the existence of two sets covering the plane, such that every horizontal line has countable intersection with the first set, and every vertical line has countable intersection with the second. Okay, but the thing is that we don't. In the physical world, we don't actually have the set of real numbers. So like, we draw down from heaven these like, information, and like we make our roads based on physics, and like we make the like odometer in the car from, using bits, like using math and like using real numbers and integrals and stuff like that. But I feel like it works for this world, but that doesn't mean that like we actually live in a Cartesian plane, or like the real line is somewhere. Which maybe that's unsettling to think, because people say, what's the continuum hypothesis for us, for our world? But it's like, we don't live in a physical, in a mathematical world. We're like, it might be unsettling to think we don't actually have the real numbers here. It's like we use the real numbers and they help us do all our physics and build our stuff, but that doesn't mean that like it actually exists there, but maybe that's unsettling. I feel like I had some more really good points, but I don't know if I can come up with them. But I just feel like there is a difference between the mathematical world and the physical world. And it's more like, to me, it's more like we get these little, like, nice little informations from heaven, and then we can do our calculations and stuff like that. But, like, we don't actually have the real numbers here. You have to go to a mathematical universe. You have to go to Gödel's constructible L. You have to go to, Cohen's world, where he showed there's Aleph too many reals. But I would say that, like, something that is kind of interesting is that, like, almost all of our measurements are transcendental. So I would believe so, like, if I measured this or something. Like, all of these little measurements would make it kind of like Walden, or like Walt Whitman or something. I don't know. Just like everything is like the transcendentalist. Like, everything is of transcendental length, because almost all real numbers are transcendental. So like, we have some like transcendental lengths here, but like, I don't know if it's like we live in a finite world and we can't have that. It's just, I think they're just very different. And I feel like we use the math to help us do stuff, but like the math is like pure or something. Okay, let me know what you think, you guys. I just think it's for the best that there's not like a rumor going around in philosophy that somehow the continuum hypothesis still hasn't been solved, and that actually, oh, the mathematicians are actually wrong because the continuum hypothesis is tied to physical reality, so it has to be true or false. And so there's wrong, because then it gets leaked down to everybody else, and everybody else thinks, oh, too bad we don't know what the continuum hypothesis is, or and it's like we do know, we do know. We know that it's a lot of different. It's a variety of possibilities. It depends on what universe you're in. But when you're in a universe, there is a definite answer. So that's just because it's like a kind of complicated and interesting answer doesn't mean that there's not an answer. And I just think that we should have the truth out there and not like think that it's because of certain mathematicians' opinions as to why we have this. It's a very cool thing to have this phenomenon. It's cool to that such a simple question like the size of the reals turns out to depend on the universe. That's interesting, right? So I think we should get the truth out there. Okay, you guys, enough of me rambling. Thanks you so much for listening, and let me know what you think, and I'll see you next week. I'm gonna try and see you guys on Fridays. I got a lot going on. So, all right. Take care and have an excellent day.